we present TreeMeshGPT, a new method for artist-created mesh using autoregressive tree sequencing. In recent years, there have been significant improvements in 3D generative models. These models can generate high-quality 3D assets conditioned on text, image, or point cloud, and have seen increasing adoption for commercial products. However, the outputs of these models are typically over-tesserated mesh that are not suitable for downstream applications. In contrast, artist-created mesh have some specific topology patterns that make them suitable for downstream applications. These patterns result in compact number of vertices and faces, have good edge flow for clean deformations, and can simplify the texture mapping process. To address these limitations, MeshGPT introduced a method to generate triangular meshes with artist-created topology using autoregressive transformer decoder. Mesh Anything later extended this approach by incorporating point cloud condition. The autoregressive generation process fundamentally relies on next token prediction, and therefore effective mesh tokenization plays a crucial role. Several tokenization methods have been explored, from a naive tokenization, CVPR, and more recent approach that leverage triangle adjacency. There are two main challenges in this autoregressive generation works. The first is long sequence resulting from the tokenization process. For example, the naive tokenization results in 9 tokens per phase. Recent methods have improved on this, achieving around 46% compression rate. However, this level of compression is still not enough for generating highly detailed mesh with many phases. The second challenge stems from the limited inductive bias in the tokenized sequence. As a result, the generated mesh often exhibit incomplete geometry and flip normals, which can cause incorrect shading. To tackle those two challenges, we propose autoregressive tree sequencing. In this method, the sequence order is retrieved from growing tree structures as opposed to the conventional next token prediction. The process is illustrated in this example. Here, we have a subset of a mesh with starting edge V0, V1. The subset of the mesh can be equivalently represented as a tree structure. The sequence is initialized by 2 auxiliary tokens to generate the starting edge. To form the next sequence, we use a depth-first search tree traversal that is tracked by a dynamic stack initialized by the starting edge V0, V1 and its twin V1, V0. The next input is obtained from the top of the stack, and since the opposite vertex is V2, we set it as the output. Afterward, we connect the opposing vertex to the initial edge to generate 2 new edges, where the directions follow half-edge data structure to enforce normal consistency. These new edges are then added to the top of the stack. We then obtain the next input from the top of the stack. Here, the next input is edge V2, V1, and since this edge is a boundary, the corresponding output is a stop label. In this situation, no new edge is added to the stack. The sequence generation then continues following the same process until the tree is fully traversed. We also propose hierarchical MLP for the vertex prediction. The naive tokenization method samples the x, y, and z coordinates using next token prediction that requires 3 sequence length for one vertex. Our hierarchical process maintains the same sampling distribution, but only requires 1 sequence length. Our method therefore offers several advantages. Since one triangular face adds 2 tree nodes, our compression rate is about 22%. Furthermore, our method only needs to predict a local extension at each generation step. This process provides a strong inductive bias, enabling our model to achieve superior results despite using significantly less training data and computation. Lastly, our method enforces a strong normal constraint that minimizes the flip normals. We train our model using Observer's dataset, and here we show some evaluations on Observer's and a real-world scan dataset. Here, we show some results where our model generates artistic mesh condition on point clouds sampled from the dense mesh of a 3D generative model. We also train a model with a finer discretization supporting higher number of phases. Thank you. Please check our paper and code from this link.